Okay, here's another in the series of extra videos where John is locked in a dark room with a bright light shining in his face and trying to explain things about MIPS. So, at the end of the Thursday lecture, I just started talking about how we'd pass a structure to a function, but passing it by reference, by passing its address. So you can see down here, we assume we've got some student object which we've loaded up with values, and here we're passing the address of that student object as the first parameter corresponding to what we've done up here, and the second parameter is going to be this WAM value. So presumably we're given some kind of floating point value in the object WAM, and that becomes the second parameter. And then we jump and link to the change WAM function. All right, let's take a look at a slightly different example. Okay, so now we've got a person structure, different to a student. This person has an ID number, a family name, which is 15 characters long, and a given name, which is 15 characters long. First thing to notice, all up, that's 30 bytes plus 4, 34 bytes. Is that a multiple of 4? No, it's not. So this structure will need some padding at the end if it's going to appear immediately before a 4-byte quantity. Okay, so the aim of the game is to pass in a pointer to a person structure, print out the ID number, print out the family name and given name separated by a comma. So you might end up with something like that. All right, okay, so here's a program which contains a main program, a call to the function showPerson, and an actual person struct. Now this one we've set up the 56 bytes, sorry, it's not 56, we set up the 34 bytes that comprise the structure as follows. So 4 bytes for the ID number, and then the family name, remember that's an array of size 15, is stored by putting a constant string into the first 9 bytes, sh 1, 2, 3, 4, 5, 6, 7, 8, followed by the null for padding, and then padded out with 6 more bytes of space to make up the 15. Similarly for the given name, that's 5 bytes, so 4 visible bytes plus a null character to close off the string, plus 10 bytes to make up to 15. Now the total size of all of that stuff is 34, not a multiple of 4, so then we round it up to the nearest multiple of 4 by aligning to the nearest 2 squared boundary. Alright, so that's the data object, the person data object. The main program, there's probably nothing unusual about that. We've got the standard prologue, the standard epilogue, push stuff onto the stack, clean stuff off the stack. The function body simply loads, the main function body simply loads the address of the person object into the argument register, and then does a jump and link to the showPerson function, which behaves like this. So that's the C code, we saw that on the exercise description. Alright, so what happens inside showPerson? Well, the standard prologue, including saving a copy of S0, because we're going to use S0 inside the function to do other stuff. And down the bottom we've got an epilogue, which is just cleaning up the stack. Alright, so the function body is about that much, right, and it's got to do all of this stuff. Okay, so mostly it's written, but I just wanted to show how do we access the components of the structure once we're inside the function. Okay, so remember that the parameter A0 was the address of the first byte in the structure, and that was passed into the function, so we grab a copy of that because we're going to overwrite the A0 register to pass stuff to the syscall. Okay, so we've got a copy of the pointer to the structure. We want to get the ID number. And so how are we going to express, give me the ID number from the structure that S0 is pointing at? Okay, so that kind of gave half the game away. The structure that S0 is pointing at, we remember that we render that in MIPS by doing that. Because we're talking about a struct, then there should be an offset involved. Now it turns out that the offset in this case is 0. So I could have omitted the 0, or I could have done that. So this address here, give me the word at the first byte of the object, the first word in the object that S0 is pointing at. So that will load it into A0. Then we set up for the syscall by loading 1, which means print an integer, and then we call syscall. Next thing, we had to print out a space, so that's simply printing a character, which is syscall 11. The next thing we want to print is the string, which is the family name. Okay, so that's obviously also in the same person struct. To access that, we dereference the S0 pointer to the struct, and then we have to add on to that the offset in the struct where the family name begins. And looking back at the definition here, the first thing in the struct is a 4-byte ID number. The second thing is the family name, so that's going to be 4 bytes from the start of the struct, which means we access it like that. Get the value of, not SP, get the value of S0 and treat that as an address, add 4, and then load that as an address. Okay, so the way that the printf, the printer string function works, you have to pass the address of the start of the string. So this expression here in MIPS assembler gives us the address of the first byte of the family string. So dereference the S0 pointer, add 4 to it, that's your start address. Then load that into A0, the argument register for the syscall, load up the actual syscall number into V0, and then call the function. Then we have to print out a comma, and the way we do that is simply load up a comma, single character, and use syscall 11 once again. Alright, next thing to do is to print out the given name. Now, remember, looking at the definition, we've got 4 bytes here, 15 bytes here. Therefore, the offset of the given name, the first byte of this array of chars, is going to be at 4 plus 15, which is 19 bytes into the structure. So we want to get 19 bytes into the structure being referenced by S0. We want to load the address of that byte into the register A0. So once again, we're using load address. And then we want to invoke the print string syscall, which is 4. And finally, we want to print out a new line character. So these are the critical bits. We've got to load in the ID number, which is a single word located right at the start of the structure. We need to load family, which is a string starting at that particular address there, 4 bytes offset from the start of the structure that S0 is pointing to. We want the address of that, and then we use that to print string. Similarly, for the given name, we want to print out. We want to load the address of the start of the given name, and then call print string to print it out. And that's pretty much it for the show person function. Let's double check that it works. And we can see that it prints out the correct ID number, correct family name, correct given name. Alright, so that's passing an object, passing a struct object by reference to a function. And you may notice one subtle difference is that I've got a space there and the actual MIPS code doesn't print a space after the comma, but that's by the by. Alright, so that kind of leads naturally into the next kind of data structure, which is a linked data structure. So remember, basically, C linked data structures are composed of structs, which are typically allocated dynamically, and each struct is contains a pointer to one or more other structures. So we've got an example here of setting up a linked list with two nodes in it. So this is the node structure, so you can see we've got a type def, so that we can just, rather than typing struct underscore node all the time, we can simply type node. And each node structure has a value, which is an int, and a pointer to the next node. Alright, so loading up a two node list is pretty straightforward. We need a node pointer, which points to the first node in the list. So we can call malloc to create an object of the appropriate size. We can set a value, set the value field in that structure that we just created, and then we want to link that to a second structure. So one way we could do that is set the next field equal to a newly created node using a second call to malloc. That structure can be referenced by that expression there. That gives you a pointer to a structure, and then we can reference the value field in that structure, and we can assign a value 2 to it. Because we're not interested in adding any more nodes, we'll also set the next field of that, the second created node, to null. So we've got a first node containing the value 1, the second node containing the value 2. Alright, so I noted earlier that SPIM doesn't have malloc, and doesn't have free, but we did implement a function which did a little bit like malloc. So to implement this code in MIPS assembler, we could do something like this. Alright, so first thing, we need to allocate a node, so we need to know how large a node is, and size of node would tell us that these particular nodes containing an int and a pointer are going to be 8 bytes long. So I could say I want to malloc 8 bytes, and once again that's the function that we wrote earlier, so go back and have a look at how that works. But assume that when that function returns, in $v0 is the address of a newly allocated object. Alright, so we want to save a copy of that newly allocated object, or the pointer to that newly allocated object, so we do a move, and that effectively does something like that. We then want to set the value field of that allocated object to 1, and so we've got a pointer to the object in S0, and the value field occurs at the start of the struct, so the offset is 0. So that expression there will allow us to store the value of 1, which we loaded into T0, into the value field in the newly created structure, which is being referenced by S0. Alright, so next thing to do, we want to call malloc again, and the reason why we have to reload the same value into $A0 is that when we call malloc, there's no guarantee that when malloc returns, this will still have the value of 8 in it. So malloc may call other functions, and you shouldn't make assumptions that it's not going to call other functions, and you certainly shouldn't make assumptions that it's not going to change the value of $A0. That's perfectly allowed by the definition or by the conventions of how we use registers. Okay, so we have to reload it, but once again say we want to malloc 8 bytes. So that's going to give us back a pointer to a newly allocated object, which we make a copy of in register T1. And I should have mentioned that the reason why we moved this into S0 is that we're going to make another call to malloc here, and we want to make sure that when this malloc returns, that this register here will still have the same value in it, placing it in an S register and assuming that all the functions follow the convention of how registers are used, means that when we come back from malloc, S0 will have its current value. Alright, so anyway, we call malloc, we get back a return value which is stored in V0, we make a copy of that into T1, and I've just noticed that I used the Unix move command rather than the MIPS move command, so this should be MOVE. So we copy V0 into T1. What we then want to do is to make the next field of the first node that we created equal to the one that we just created. So T1 contains a pointer to the newly created object, and we want to place that in the next field of the object that S0 is pointing to, and the next field is at offset 4. So that's going to store the contents of T1 into this particular location, which corresponds to the next field of S0. The other thing that we wanted to do was we wanted to load the value 2 into this newly created object. When I wrote in C, I had to write S0 arrow next arrow value. But in this case, we've got a pointer direct to the next object, so I can just use that. And the value is at offset 0, so we can say that, and store the value 2 in that location. The other thing we wanted to do was set the next pointer in the second object to be null. Now we can assume in MIPS assembler that the value null is going to correspond to the value 0. So if we store the value 0 into the next field in the object that T1 is pointing to, that effectively gives us that result there. Alright, so $0 at the end of all of this, $0 is pointing to a node, and that node contains a pointer to a second node that we created. So essentially it's the same as what we've done here. Alright, so perhaps we want to implement a function that will display a list. So we had a function to show a person before. That was showing just the values contained in a single struct that was being referenced by a pointer. In this case, we've got a pointer to a struct, but that struct contains a pointer to another struct and potentially to another struct and another struct and another struct. And the standard way of traversing a list like that is to have a cursor start at the first node and then go until we reach the end of the list, where the last node is always going to have a null in its next field, and when we grab a copy of the next field, current will be set equal to null, and that will terminate the loop. And how do we move from node to node? We do it like that. So we set the cursor, or the current node, to be equal to what the current node is referring to as the next node. So at this point, current tells us the current node. This gives us a pointer to the next node, and we assign that to current. So we've updated the current node, if you like. Right, for each node, we print out its value, and we want to print a comma, but only if it's not the last node. If it's the last node, we don't have to print any comma. We simply want, if it is the last node, the loop is going to terminate, and then we'll print a new line character. So for the thing that we created above, for this code here, this ought to produce 1, 2. And because we've got a variable that runs through the body of the function, we need to put it somewhere. Since there's potential that we're going to call other functions, we'll assign that value to $S0. So $S0 is effectively representing current. All right, so let's take a look at that. Now this one I just made a copy from the student example, so I might just change it. And here I won't bother using malloc. I'll actually just create these 2 nodes by hand. So node 1 is going to have a value of 1 and a pointer to the second node. So if I load the address associated with node 2 into there, that effectively gives me a pointer to this node, which is going to contain the value 2. And let's actually make 3 nodes just for fun. Right, so that can point to node 3. And let's put the value, just to be different, put the value 4 there. And then we'll terminate the list by storing a value null in the next field of the third node. So the first field is always value, and the second one is next. So that applies to all of those things. Alright, so for the main program, what we're going to do is we're going to show the list, and we're showing the list that starts at node 1. Node 1. So we load the address of node 1 into A0, and we call the function show list. Oops. Alright, so let's go down here. So show list has to do all of this, and of course it's a function, so it has a prologue and a body and an epilogue. So remember that I said we were going to use S0 to represent this, so we need to save that at the start of the function as part of the prologue. Alright, so for the body, let's see. So first thing we needed to start current at the start of the list. The start of the list, or a pointer to the first node in the list, comes into this function through the register A0. So we make a copy of that into S0. Next thing to do, start implementing the loop. So here's the extent of the loop. We've got a for loop that starts here and ends down here. Alright, and the stuff in the middle is really just what's left over from the printing the student. So I might just delete that. Okay, a lot of it, the rest of it stays the same. Alright, so how do we know that the loop has to continue? Well, it continues while current is not equal to null. Therefore, it terminates when current is equal to null. So we can check whether current is equal to null by doing a branch on equal. Current is S0, null is just 0, and in that case we go to N4. So that would handle our loop. Next thing to worry about, we've got to load the value that's stored in the current node. And since we're going to print that, we'll load it into A0. All right, the current node is being referred to by S0, and we want to get the value field from that. Remember, the value field is at offset 0. So if we do that, that will load the value stored in the current node into the register A0. We can then invoke $V0. We can invoke syscall1, and that will print out the value that we loaded here. All right, next thing we have to worry about, do we need to print a comma? Not always. We only want to print a comma if, so let's just put some space there. We only want to print a comma if current next is not equal to null. So one thing we could do at this point, we could actually load the value of current next, since we're going to need that when we go around the loop anyway. So maybe what we'll do here is update S0 to contain the next field from the current S0. So effectively what this is doing, it's saying current is assigned current next. I mean, one thing to note about that, this C expression maps quite nicely into a single line of MIPS assembler. So you can kind of guess that maybe manipulating linked data structures like this would be relatively efficient. All right, so having loaded that, I guess what we could do is we could say if current is equal to null, then we can just break. So we're kind of duplicating what we had above, but I guess that doesn't matter too much. You can tell I'm making this up as I go along. So if the new value of current is equal to null, then we branch to the end of the for loop and we're done. Oops. All right. If that doesn't happen, then we clearly want to print a comma. So I should make the comments consistent. And then what we want to do is we want to advance, well, in the C code, we want to advance current to the next node, but we've already done that. We did that up here. So the only thing that we really need to do is go back to the top of the for loop. You might say it's a bit redundant having a test up here if you've also got a test down here. Maybe, but having a test here will cater for the case where the initial value of L or current is null, because you always have to allow for the fact that you might have an empty list. All right, well that looks pretty much like what we need. So let's see if that's actually correct. So if it is correct, it should print 1, 2, 4, separated by commas. So there you go. Okay, so a loop, for loop, jump back to for loop, check whether we've reached the end of the list because S0 has become null. If that's true, if that's not true, then we print the value of the current node, accessing the value like that, and then we try to go forward to the next node in the list. If it turns out there is no next node, then we may as well exit the loop at this point. Otherwise, we print a comma and then go back to the top of the loop. So that's a bit of linked list manipulation in MIPS assembler. And that, I think, will do for this video. We'll talk about link structures in MIPS, or implementing something like Melican free next time.